So, yeah, our paper is about a separation logic for negative dependence, and my name is Jialu. This is a collaborative work with Professor Marco Gaboardi, my advisor Justin Su, and Professor Joseph Tassarotti. So why do we want to reason about negative dependence? Let's look at a simple motivating example. Say that we are throwing balls into bins, where each bin can only hold a certain number of balls before overflowing. This toy example models hash algorithms, so it's natural to wonder what's the probability that there exists more than at least two bins that overflows. Intuitively, it is unlikely for many bins to overflow together, because if one bin overflows, that means more balls have gone into that bin, leaving less balls going to other bins, so it's less likely for other bins to also overflow. Mathematically, we can describe this as the bin's overflowing status is negatively associated. Negative association is a kind of negative dependence, and this will be the focus of our paper. But because its formal definition is quite technical, so we won't present this in the talk. Instead, we'll introduce its properties when needed. Roughly, it describes a scenario where when one random variable in the set attains a lower value, the other random variables in the set tend to attain higher values. One property of that is that it generalizes independence. So independent random variables are negatively associated. So suppose for a second that we're reasoning about sum of independent random variables. Then there is a standard tool called concentration bonds. Suppose y is sum of n independent random variables yi. Then concentration bonds give us a formula f. Depending on n and the constant m, that upper bounds the probability that the value of y deviates from its expectation for more than m. However, the overflowing status of our bins is negatively associated, but not independent. Luckily, concentration bonds, many concentration bonds, they also generalize for any random variables. So we can apply a concentration bond to the sum of the bin's overflowing status, and with some rearranging of the terms, we can bound this probability. Now, a question is that how to prove negative association formally? For that, we think about using probabilistic separation logic. So our plan is to transform these processes into probabilistic programs, and then we use probabilistic separation logic to verify them and reason about negative association arising in that process. And our contribution is a logic called LINA. Specifically, we contribute to three aspects. So the first aspect is an assertion logic with a separating conjunction for asserting negative association. Built upon that assertion logic, we develop a program logic called LINA, short for a logic for independence and negative association. LINA is a separation logic for reasoning about probabilistic programs. Furthermore, we demonstrated applications of LINA in verifying various probabilistic data structures. One of the examples is verifying Bloom filter. In the rest of the talk, we'll first give some brief background on separation logic. Then we'll go through our contributions in each aspect one by one. So separation logic is a flexible framework to reason about sharing and separation. It has two layers, the assertion logic layer and the program logic layer. The assertion logic in separation logic is often taken to be the logic of bunched implications, abbreviated as BI. BI extends standard propositional logic with two extra formulas. So these are the formulas for the standard propositional logic. This new formula is read as P star Q, and this is read as P magic wand Q. The star is also called separating conjunction, and as the name suggested, it is often used to reason about separation, of different states. Built upon the assertion logic, um, the program logic of separation logic has judgments of horse style. So here, the judgments are in this triple. P and Q are assertions from the assertion logic, and C is a program. Putting together, this triple means that starting from any program states that satisfies P, if we run the program C, that then we'll end in a program state that satisfies Q. Among many program rules of separation logic, the signature one is a frame rule. It allows compositional reasoning in separation logic. We'll show the frame rule of our logic later. As we said, LINA is a separation logic for reasoning about probabilistic programs. So in the assertion logic of LINA, we take the states to be distributions over program memories. So we make assertions to these states. In a prior work, Bart et al. Developed a logic with independence conjunction on these states. So they define the semantics of this separating star such that this formula would assert probabilistic independence. So here we would use the angle brackets as a notation, angle brackets around a program variable as a notation to mean that that program variable is in the domain of the distribution. So this formula says that x1 is in the domain, star xn is in the domain. We extend their logic with a negative association conjunction. So we introduce a new star, the Na star, for asserting negative association. The main challenges in our extension is to find a good semantics for the Na star. As other separation logics, we develop a cryptic semantics for our logic. So to define the meaning of a new conjunction, what we do is to define a new binary operator on the set of states. And then a state would satisfy this P star Q. If we can find two other states, one satisfies P, another satisfies Q, and that we can use the binary operation we just defined to compose them together to get back the original state, as this diagram shows. For example, in the prior work, when defining the independence conjunction, they define this binary operation to be independent product. However, it is subtle to define O plus for the Na star. For one thing, given two distributions, F and G, there exists multiple, while there exists only one independent product of F and G, there exists multiple joint distribution of F and G where their domains are negatively associated. The intuition is that because Na is weaker than independence. So this plus has to be non-deterministic. For that purpose, we would, instead of using equality here, we would use belong to. Furthermore, some natural choices of this plus don't validate required axioms. One natural choice fails unit existence. For another one, the associativity of this O plus is unclear. To solve that challenge, our solution uses a new negative dependence notion called PNA, short for partition negative association. PNA generalize NA. So NA is a relation on a set of random variables. PNA is a relation on a partition of a set. So here I show a partition where each component of the partition contains only one element. For this, a PNA for this partition is equivalent to the NA of the base set. However, we can also talk about PNA of other partition of the same base set, and PNA for this partition would be weaker. So what we actually do is to define the separating conjunction to capture PNA. But because PNA generalizes NA, our logic can also be used to reason about NA. For example, there are many interesting properties of PNA, and they can all be encoded as valid axioms in our logic. Some examples are, so this states that PNA also generalize independence, that any partitions of independent random variables are also PNA. This is similar, but it states if we start with two PNA partitions and we take an independent union of them, the resulting partition is also PNA. The third one is more interesting. It says that if we have a PNA partition, suppose we have each component of the partition contains only singleton elements x, y, z each. Then say we apply a monotonically increasing map, say addition, we add x and y together and put them into another partition. Then x plus y and z is also PNA. And these can all be encoded as axioms in our logic. Now, using that assertion logic, we develop a program logic of LINA. As we suggested before, our judgments are in Hoare style. Here, the program C is a probabilistic program. Specifically, we take standard imperative language plus a sampling command. Our program logic LINA is a conservative extension of the probabilistic separation logic developed by prior work, so all their program rules are valid in our logic. We generalizes several of their rules, but our most interesting contribution is a new frame rule. This is the frame rule in their logic for independence. It says that if we have a judgment saying phi, run C, and then psi, their frame rule allows you to conjunct assertion alpha if the free variables in alpha is independent from the free variables in phi and psi, and that the program C does not modify free variables in alpha. This rule allows you to do compositional reasoning of independent components in a distribution, and that kind of makes sense. You wonder if we can generalize that to NA frame rule by replace this by NA star, but this is not the case. However, on a special case, when in the post condition, we are asserting that a program variable y is in the domain and that y can be obtained from a monotonically increasing map on the domain of phi. In this special case, we also have a frame rule that allows us to do compositional reasoning of negatively associated components in a distribution. Now, we'll see applications of our program logic to the motivating example. And when doing that, we'll see more program rules. We encode our example as the following probabilistic program. Assume that the number of balls in bins started with 0, and we represent that as a vector stored in the program variable bins. When each ball comes, we sample a bin uniformly at random, and in the code, this is accomplished by sampling from one hot vector uniformly at random. A one hot vector is a vector with 0, 1 entries, where there's exactly one entry being 1 and all other entries being 0. So the entries being one is the being gets selected. And after select the being, we update the being's count. At the end of the program, we check if each being overflows. What we are going to establish is that it's the looping variant, saying if we start with the being's count negatively associated, then after one iteration, they will still be negatively associated. Let's copy the code here. So the first step is a deterministic assignment to n, so it doesn't touch beings. So we can just copy over. Here, we sample from a distribution, and that distribution, when sampling, we do not use any program variables mentioned here. So by random R sample rule, the newly sampled distribution will be independent from the current distribution. And this is notation for saying that the program variable new stores a vector whose entries are distributed as a one hot distribution. And this is a fact that saying one hot distributions entries in one hot distributions satisfy negative association, and we can encode that as an axiom in our logic. By using that, we can state that the entries in new are negatively associated. As we said before, independent union of negatively associated sets are also negatively associated. So we can replace this independence conjunction by the Na star. In the last step, we have an addition. An addition is a monotonic map. The rule looks quite complicated, but it basically says because we are adding the ice entry in bins with the ice entries in new, and the map is a monotonically increasing map. So the NA relation is preserved. So we establish the loop invariant. And this is about the end of our talk. For more in the paper, we also present MBI logic. This is a byproduct when we are constructing an assertion logic for asserting negative dependence. MBI logic is a sound and complete extension of BI with multiple separating conjunctions. And our assertion logic is a model of it. Also, more program rules of LINA. We also shows applications to various probabilistic data structures like Bloom filter and permutation hashing. And thanks. This is the end of my talk.